notation at the beginning. N means it's a standard, it's a normal distribution. The first number 0 tells you your mean is 0. The second number 1 tells you that your standard deviation is going to be 1. It's actually your variance, but if your variance is 1, then your standard deviation is 1 as well. Okay? And in this case, this would be a standard normal distribution. And a standard normal distribution deals with z-scores, because z-scores, which we're just reviewing, is how many standard deviations you are above or below the mean. So if we look at our last example, 4 would be 1 standard deviation above the mean. 4 would have a z-score of 1. 4.4 is 2 standard deviations above the mean. It would have a z-score of 2. So now in our next example, we want to find the probability that someone has a z-score less than 2.68. So if we draw a picture with our z-scores, which is our standard normal distribution, the mean of 0, our nice bell curve, 3 standard deviations above and 3 standard deviations below. We want to find the probability that it's less than 2.68. If you had to give an estimate using the 68.95, 99.7 rule, what percentage do you think that would be? Quite a bit. High 90s. Okay, so we can go to our calculator, go to our distributions, normal CDF. Whoops, get out of this mode first. Clear everything. Normal CDF, we have no lower, so we can leave the -1 e to the 99 as a very big lower number. Our upper was, now I've forgotten it, 2.68. Mean is 0, standard deviation is 0. Go down and paste that in. And yes, it was very, very close to 100%. To 3 sig figs, 0.996 or 99.6% chance. Yeah, I'd like you to try the next two. Here, I'll put up the answer for this one just so you can double check. And the last one, did you get that answer? Awesome. Oh, you didn't see that one? You just skipped it? Nice. Good strategy. Save time. So the next types of questions that you need to be able to do, which were also on your take-home quiz, is if you're given the area or you're given the probability, could you find the score? And this is another button on your calculator called the inverse norm button. And what it does is it says if you know the percentage, you can work your way backwards to find out what the score would be. So here's an example. If the average on a test was 60% and the standard deviation in the class was 7, what score would separate the top 10% of the class? So if we draw a picture of this, or if we draw a picture of this normal distribution, we've got 60 right here in the middle, 3 standard deviations above, 3 standard deviations below. Okay, and looking at these scores, almost 100% of people scored between 39% and 81%. Almost nobody got over 81%. This is not a very good result of a math test. Okay, we want the top 10%. So somewhere here, if we're shading, I want to shade in purple. Nice. Somewhere here, this shaded part is 10%. Now, when we use our inverse norm button, we always start by putting in the percentage, and the percentage goes right here. And the calculator needs to know, like, when you put in 10%, is it like, well, how do I know if it's the upper 10% or the lower 10%? Because that would give me 2 different scores. So the calculator always does the percentage from the left. So if I wanted to figure out the top 10%, well, that means that there's 90% to the left of that. And so when we go to type it into our calculator with the inverse norm, and we'll just find our inverse norm button here, number 3. We put in the area, which is the percentage from the left, 90%. In this case, our mean was 60, and our standard deviation was 7. And we find out that the score of 69.0 or 68.97, that's what would separate the top 10% of the class. Yes? A left, right, center? Oh, I don't have that on mine. Let's see. So how many people have that left, right, center when they went to inverse norm? So what I'd like you to try, so on mine it always comes from the left. I want to see if you have that left, right, center, go from the left, do 90%. Go from the right, do 10%. Go from the center, do 40%. See if you get the same answer each time. How many people have the left, right, center on their calculator? Just one? Well, then that's not very helpful. Special. Does anybody else have a light aqua cover? No? Okay. Man. They're different. Okay, then we'll have to figure out what that is. So this is your Z-score formula. And a Z-score is standardizing the data. So for example, if we take that math test that we just had with the mean at 60 and the standard deviation of 7, okay, if someone scored a 67, they're 1 standard deviation above the mean. If we look at the formula, the Z-score formula says your score was 67, the mean was 60, the standard deviation was 7, your standard score is 1. Your Z-score is 1 because you are exactly 1 standard deviation above the mean. Does that make sense? So if you want to find out where you fit, you could calculate your Z-score And then that would be a way of comparing your result to somebody else's. And where this is used is especially when, let's say you're applying to an American university and you wrote your SATs or something like that. And someone else is trying to get into the same university, but they wrote their SAT the year before you did. And everybody knows that your year, the SAT was harder than that year. The world average or the average was lower. And so you're like, this isn't fair. They're going to get in because they got a better score than me, but I wrote a harder test. So how can they, and so they also recognize that's not necessarily fair, right? If you write a harder test than somebody else and they're comparing the two, how do they compare which score is better? Well, if they look at a normal distribution and say, oh, your z-score was 1.9. You were 1.9 standard deviations above the mean in the year that you wrote it. And they were only 1.2 standard deviations above the mean in the year that they wrote it. Even though their score is higher, statistically, you did better. Because on that harder test, you ranked in a higher percentage. And all things considering, and again, when you collect enough data, you say, okay, every year people are generally the same. So being in the top percent in 2018 is better than being in the top 20% of 2017. And so these standardizing the data can help you in comparing. All right. Lifetime of a particular make of television is normally distributed with a mean of 8 years. There's our bell curve. We know the mean is 8. The chances that the tube will not last 5 years, so somewhere on here I can put the number 5. I can take out a fancy crayon. I'll use this color. Oh, nice. And this percentage right here is 5%. What's the standard deviation? So we run into a question where we have a percentage, so that makes us think about using inverse norm, but we already have the score for that percentage, which is 5. And the problem is we don't know the standard deviation, so any of our formulas that we plug in will give us no answers. So what we do is we go and say, I could redraw this same thing as a standard normal distribution with z-scores. The only problem here, I could shade this again, label that as 5%. And if I have a standard normal distribution, then I know 1, 2, 3, -1, -2, -3. Ooh, I hope that percentage is somewhere in there. I think I might be off a little bit. Let's just, there we go. If I draw my standard normal distribution, then I don't know the score. If I draw my normal distribution, I don't know my standard deviation. But from my standard normal distribution, I can use my inverse norm button. So if I go inverse norm, because I have the percentage, the area, clear that out, is 0.05. My mean is 0. My standard deviation is 1. It should be at -1.64. I'm going to store that as x. Yes. So what I did in the second part is I drew a standard normal distribution. Okay? Now, for every set of data that you have, you can always convert it to a standard normal distribution. And that was sort of what I was talking about in the last slide when I said, if you scored a 67, then you're one standard deviation above the mean. So we could transfer all the data that we have here to 0, 1, 2, 3, right? If you scored a 74, your score is a 2 instead of a 74. So it's a way of standardizing it between, you know, having a mean of 0 and standard deviations of 1. So any set of data that you have, you could transfer it to this. And you can transfer it to that using this formula, which gets you z-scores, and the z-scores are just how many standard deviations above and below the mean you are. So in our example, we had the mean of 8, and we knew 5 years was a 5% chance. I'm just standardizing it and going to my inverse norm 0.5, 0, and 1 to find that my z-score was negative 1.64. Yes, thank you. 0.05. And now that I have that, we could say, well, there's a formula for changing the 5 to the negative 1.64. There's a way of standardizing things. The way that we standardize things is with this formula. And now that I look at that formula, I know my actual score was 5. I know my mean was 8. And I know that my standard normal score was 1.64. And the question was asking me to find the standard deviation. And so my standard deviation, if I solve this, will be negative 3 divided by negative 1.64. I guess I wouldn't have needed to store it because I can just collect that answer from there before. And my standard deviation was 1.82. I guess I should use approximation signs here and here as well, because I was using that rounded 1.64 in those equations. Yes. Yes, in this case, the units were years. Thank you. Do you need me to go back? It was good? So given a random variable is normally distributed with a mean of 2 and a variance of 9, and sometimes they'll write the variance that way 3 squared. Why? Because then you can really see the standard deviation is 3. Can draw a picture of what's happening. And so the question is here, would we use normal CDF or inverse norm? Normal CDF, because you're finding the probability. But I want to look at the summary right at the end. For normal distributions, you can kind of categorize things into 3 types, right? Right? If you want to find a probability, and it can be given a z-score or just a regular score, you're going to use your normal CDF. If you're wanting to find a z-score or any score, if you want to find the score and you know the probability, that's where you're going to use inverse norm. And the last one that we did with the television is sometimes you want to find the mean or standard deviation. And in those cases, you're going to have to use your inverse norm first to find a z-score. And you have to use the inverse norm with a standard normal distribution. And then use the formula to figure out either the mean or the standard deviation. So with normal distributions, these are the 3 main types of questions. Here are the answers for those last 2 that you're doing on your own.
We have to draw it?
You don't have to draw it. I like the visual that drawing it does. And the last one